Have you ever stopped to think about what it really means to connect two oceans? I mean, we're not talking about digging a ditch in your backyard here. We're talking about cutting through an entire continent. And not just any continent. We're talking about one of the most hostile, unforgiving pieces of land on Earth. Welcome to the Isthmus of Panama, just 50 miles wide. That's it, 50 miles separating the Atlantic from the Pacific. Sounds simple, right? Well, let me tell you, nothing about this place was simple. Picture this. You're standing in the middle of the Panamanian jungle in the late 1800s. The air is so thick with humidity, you feel like you're breathing soup. The temperature? A relentless 90 degrees Fahrenheit day after day. Rain doesn't just fall here, it attacks. We're talking about 200 inches of rainfall per year in some areas. To put that in perspective, London gets about 25 inches annually. Yeah, that's almost 10 times more water. But here's where it gets interesting. Why did engineers even consider this nightmare of a location? Because geography is cruel in its logic. This narrow strip of land was the only realistic option to connect the world's two largest oceans without sailing around the entire South American continent. A journey that added thousands of miles and weeks of travel time. Now let's talk about what they were actually dealing with on the ground. The Panamanian terrain wasn't just difficult, it was almost perfectly designed to destroy any construction effort. First, you had the Continental Divide running right through the middle. This meant mountains, not gentle hills, actual mountains rising hundreds of feet above sea level. The highest point, the Culebra Cut area, sat at about 330 feet elevation. Think about what that means for a moment. If you wanted to build a canal at sea level, which was the original French plan, you'd have to excavate down through solid rock for hundreds of feet. And I'm not talking about nice, stable granite. This was volcanic rock, clay, and unstable sediment that had a nasty habit of sliding back into any hole you dug. The geological composition was an engineer's nightmare. The rock formations were fractured and weathered, meaning they could collapse without warning. Add torrential rainfall to the mix, and you've got landslides that could bury months of work in a single afternoon. Historical records show that some slides moved millions of cubic yards of material, enough to fill several football stadiums. But wait, there's more. The Chagres River, one of the most powerful rivers in Central America, flows directly through the proposed canal route. During the dry season, it's manageable. During the rainy season, it transforms into a raging torrent carrying 10 times its normal volume. Early engineers measured flow rates exceeding 100,000 cubic feet per second during floods. That's like trying to control Niagara Falls while simultaneously building through it. And here's something most people don't realize. The jungle itself was an active enemy. Dense tropical vegetation didn't just make surveying difficult, it made it nearly impossible. Trees grew so thick that visibility was measured in feet, not miles. Every time workers cleared an area, the jungle began reclaiming it within days. Vines, roots, and undergrowth created a living obstacle that fought back against every machete stroke. The wildlife added another layer of complexity. Venomous snakes, aggressive insects, and predators made every workday dangerous. But the real killers were microscopic, mosquitoes carrying malaria and yellow fever. We'll dive deeper into that nightmare in later chapters, but understand this. The environment itself was actively trying to kill anyone who worked there. So why here? Why this specific location? Because engineers calculated that the Isthmus of Panama offered the shortest distance between oceans, the most favorable overall terrain compared to other Central American routes, and, crucially, the Chagres River, despite its challenges, could potentially be harnessed as part of the solution rather than just an obstacle. The French learned this the hard way. When they arrived in 1881, they brought experience from building the Suez Canal in Egypt. But Suez was essentially a flat desert, completely different from Panama's vertical jungle. The French expected to replicate their success. Instead, they discovered that every assumption they'd made was wrong. The sheer scale of Earth movement required was staggering. Engineers estimated they'd need to excavate over 100 million cubic yards of material, and that was a conservative estimate. For context, that's enough dirt to bury the entire island of Manhattan under 14 feet of soil. Temperature and humidity didn't just make work uncomfortable, they made metal tools rust overnight, degraded materials, and created conditions where equipment failed constantly. Steam-powered machinery, the cutting edge of 1880s technology, barely functioned in the tropical heat. Boilers overheated, metal expanded and contracted, and maintenance became a full-time battle. But here's what fascinates me most. Despite all these challenges, despite the geological chaos, the climate extremes, and the hostile environment, someone looked at this place and said, "We can do this." That kind of ambition, some might call it madness, is what drives human progress. The question wasn't whether it was difficult, it was whether it was physically possible. Could human engineering overcome nature's obstacles? Could technology triumph over terrain that had remained unchanged for millions of years? As we'll see in the next chapters, answering that question required revolutionary thinking, catastrophic failures, and innovations that changed engineering forever. So the French arrived in Panama with all the confidence in the world. And why wouldn't they? These were the same engineers who had just pulled off one of the century's greatest achievements, the Suez Canal. They had the expertise, the funding, and the reputation. What could possibly go wrong? Well, pretty much everything. Let me take you back to 1881. Ferdinand de Lesseps, the visionary behind Suez, stood before investors and declared that Panama would be even easier than Egypt. He estimated the project would take 8 years and cost about $132 million. Keep those numbers in mind, because they're about to become tragically hilarious. Here's the fundamental mistake. De Lesseps insisted on building a sea-level canal. No locks, no elevation changes, just one straight cut from ocean to ocean, exactly like Suez. Sounds logical, right? After all, it worked in Egypt. But remember what we discussed in Chapter 1? The continental divide sits right in the middle of Panama, rising over 300 feet above sea level. That meant excavating down through mountains of unstable rock and clay. The French basically looked at a mountain range and said, "We'll just dig through it." The sheer audacity is almost admirable, if it wasn't so catastrophically miscalculated. The excavation began at the Culebra Cut, and immediately problems emerged. The geological surveys had been inadequate. Nobody fully understood what they were digging into. The volcanic rock wasn't uniform. One day you'd hit hard basalt that shattered drill bits. The next day you'd encounter soft clay that collapsed as soon as you removed it. It was like trying to dig a hole in wet sand while someone kept filling it back in. And those landslides I mentioned? They weren't occasional annoyances. They were constant catastrophes. Workers would spend weeks excavating a section only to have a tropical downpour trigger a massive slide that buried everything overnight. Historical records document slides that moved over 1 million cubic yards of material in minutes. Imagine watching a month's work disappear before your eyes because the rain decided to show up. But here's where the French approach really fell apart. They brought the wrong equipment for the job. Their excavators and steam shovels were designed for the desert conditions of Egypt, dry, stable sand. In Panama's humidity, machinery corroded rapidly. The constant rain turned work sites into mud pits where heavy equipment simply sank. Replacement parts took months to arrive from Europe, meaning broken machines sat idle while projects stalled. Let me give you some numbers that really illustrate the scale of this failure. The French excavated approximately 78 million cubic yards of material over their 8 years in Panama. Sounds impressive, right? Except they needed to remove at least twice that much. And that's not accounting for all the material that kept sliding back into the cuts. They were literally losing ground. The costs spiraled out of control. That initial estimate of $132 million? Try over $300 million, and they still didn't finish. Investors back in France began losing confidence as year after year passed with no completion in sight. The entire financial structure of the project started crumbling. But the real tragedy wasn't financial, it was human. We need to talk about the death toll, because this is where the French failure becomes truly devastating. Conservative estimates put the death toll at around 22,000 workers. 22,000. Other historians suggest the number might have been as high as 30,000. Most of these deaths weren't from construction accidents. They were from disease. Yellow fever and malaria ravaged the workforce with horrifying efficiency. The French had no understanding of how these diseases spread. They didn't know mosquitoes were the vectors. Hospital wards placed water-filled containers under bed legs to prevent insects from crawling up, unknowingly creating perfect mosquito breeding grounds right next to sick patients. They were literally making the problem worse while trying to help. Workers arrived healthy and were dead within weeks. The mortality rate was so high that coffin making became one of Panama's busiest industries. Ships arriving with fresh workers would often leave with more coffins than passengers. Imagine being a worker watching ship after ship depart with your dead colleagues, knowing you might be next. The psychological impact was crushing. Morale collapsed as disease spread faster than construction progressed. Experienced workers fled back to Europe. Recruitment became nearly impossible as word spread about the death sentence of working in Panama. The project became known as a graveyard rather than an engineering marvel. Here's what's important to understand. The French didn't fail because they were incompetent. They failed because they misunderstood the fundamental nature of the challenge. They treated Panama like another Suez, but these were completely different environments requiring completely different solutions. So what did the world learn from this disaster? First, you cannot simply transplant engineering solutions from one environment to another. What works in a flat desert won't work in a mountainous jungle. Second, geological surveys matter. You need to understand what you're building through, not just assume it'll cooperate. Third, worker health isn't just a humanitarian concern, it's an engineering necessity. Dead workers can't build canals. But perhaps the most valuable lesson was this. Maybe a sea-level canal wasn't the answer. Maybe the mountain didn't need to be completely removed. Maybe there was another way, a way that worked with the terrain rather than against it. By 1889, the French effort collapsed entirely. The company went bankrupt, de Lesseps faced criminal charges for mismanagement, and the dream of a Panama Canal seemed dead. Equipment rusted in the jungle, excavated cuts slowly filled with vegetation and rainwater. It looked like nature had won. But those 8 years of failure weren't wasted. The data collected, the lessons learned, and the infrastructure left behind would prove invaluable. Because 20 years later, someone else would look at this same impossible challenge and think, we can do this, but we'll do it differently. Here's a question that might surprise you. What was the single most important breakthrough that made the Panama Canal possible? Was it the steam shovels, the explosives, the innovative lock designs? Nope. It was mosquito nets and window screens. I know, that sounds ridiculous. But stick with me here, because this chapter is about how medical science became just as crucial as engineering excellence. Without solving the disease problem, all the excavators and concrete in the world wouldn't have mattered. When the Americans took over the canal project in 1904, they inherited more than just rusted French equipment and half-finished cuts. They inherited a death trap. Yellow fever and malaria had killed tens of thousands of French workers, and they were still waiting in the jungle, ready to kill thousands more. Enter Dr. William Gorgas. Now, this guy doesn't get nearly enough credit in history books. He was the chief sanitation officer for the canal project. And honestly, He might have been more important than any engineer on site, because Gorgas understood something revolutionary. Mosquitoes were the enemy. Let me set the scene. It's 1904, and germ theory is still relatively new. The idea that tiny insects could transmit deadly diseases was controversial. Many people still believed diseases came from bad air, or miasma. Even some of the canal administrators thought Gorgas was wasting time and money on his mosquito crusade. But Gorgas had seen this work before. In Havana, Cuba, just a few years earlier, he'd helped prove that controlling mosquito populations could eliminate yellow fever. He'd seen a city transform from a disease-ridden nightmare to a safe place to live. And he knew, absolutely knew, that the same approach could work in Panama. So what exactly did Gorgas do? First, he declared war on standing water. Mosquitoes breed in stagnant water, so his teams went absolutely everywhere, and I mean everywhere, eliminating any place mosquitoes could reproduce. They drained swamps, filled in puddles, covered water containers, and poured oil on any water surface they couldn't eliminate. The oil created a film that prevented mosquito larvae from breathing. Think about the scale of this operation. Panama receives over 200 inches of rain annually in some areas. Every rainstorm creates thousands of potential breeding sites. Gorgas employed entire brigades of workers whose only job was mosquito control. They inspected every building, every yard, every construction site, weekly. Homes and buildings underwent mandatory fumigation. Workers would seal a building, burn pyrethrum powder inside to kill adult mosquitoes, then ventilate it. This wasn't optional. It was enforced. If you lived or worked in the canal zone, your space was getting fumigated, whether you liked it or not. But here's where it gets really interesting. Gorgas understood that different mosquitoes transmitted different diseases. The Aedes aegypti mosquito carried yellow fever and preferred clean water in urban areas. They'd breed in water barrels, cisterns, even flower vases. The Anopheles mosquito carried malaria and preferred dirty, stagnant water in rural areas like swamps and puddles. This meant two completely different control strategies running simultaneously. Urban areas got intensive screening programs. Every window, every door, every ventilation opening got covered with fine mesh screening. Hospitals were screened completely, creating the first truly mosquito-proof medical facilities in the tropics. For malaria control in rural areas, drainage was key. Gorgas's teams dug miles and miles of ditches to drain swamps. They cleared vegetation from around water bodies because mosquitoes need plants for shade and a shelter. They even introduced small fish into water bodies that couldn't be drained. These fish ate mosquito larvae. The investment was massive. In the first year alone, Gorgas spent over $1 million just on sanitation efforts. Canal administrators were furious. They wanted that money going toward excavation, not bug control. There was serious pressure to fire Gorgas and abandon the mosquito program. But then something remarkable happened. The death rate started dropping dramatically. In 1906, yellow fever killed over 100 workers. By 1907, 0 deaths, not one. Yellow fever was effectively eliminated from the canal zone within 3 years. Let that sink in. A disease that had killed thousands of French workers was completely controlled. Malaria took longer because it was more widespread and the mosquitoes harder to eliminate. But even malaria deaths dropped from hundreds per year to just dozens. The hospitalization rate from malaria fell by over 80% between 1906 and 1913. Here's a statistic that really drives this home. During the French effort, the death rate was about 60 deaths per 1,000 workers annually. Under American control with Gorgas's programs, it dropped to about 6 per 1,000. That's a 90% reduction in mortality. But the impact went beyond just preventing deaths. Healthy workers are productive workers. When you're not spending half your workforce in hospital beds fighting fever, projects actually progress. Morale improved dramatically when workers realized they weren't signing their own death warrants by coming to Panama. Gorgas also revolutionized hospital care in the tropics. He built modern hospitals with screened wards, proper sanitation, and trained medical staff. These weren't just treatment centers. They were research facilities where doctors studied tropical diseases and developed better treatments. The screening program alone was an engineering marvel. Workers installed screens on over 5,000 buildings. Every house, every barracks, every office in the canal zone became a fortress against mosquitoes. They even screened entire trains that transported workers and materials through the zone. And here's something most people don't know. Gorgas didn't just protect workers, he protected their families. Women and children living in the canal zone received the same protections. This meant workers could bring their families without fear, which improved long-term retention and created stable communities rather than transient labor camps. The success in Panama became a template for tropical medicine worldwide. Gorgas's methods proved that humans could live and work safely in tropical environments previously considered deadly. This opened up development possibilities across Africa, Asia, and South America. But here's the crucial point. None of the engineering achievements we'll discuss in the next chapters would have been possible without this medical revolution. You can't build a canal if your workers keep dying. You can't maintain complex machinery if everyone's too sick to operate it. You can't sustain an 8-year construction project if you can't keep anyone alive long enough to see it through. So when you hear about the Panama Canal's engineering triumphs, and we'll get to those spectacular innovations, remember that it all started with understanding that the smallest enemy required the biggest solution. All right, let's talk about the decision that literally made or broke the entire canal project. And I mean that literally. Without this choice, the Panama Canal simply wouldn't exist today. So here's the million-dollar question. How do you move ships across a mountain range? Remember, the French had insisted on a sea-level canal. Just dig straight through, ocean to ocean, no elevation changes. We already saw how spectacularly that failed. But when the Americans took over in 1904, they faced the same fundamental problem. The continental divide sitting stubbornly in the middle of their route, hundreds of feet above sea level. The debate that followed was intense. And I'm not talking about a polite engineering discussion over coffee. This was a political battle that reached all the way to the U.S. Congress, involved some of the era's greatest engineers, and literally determined the fate of one of history's largest construction projects. On one side stood the sea-level advocates. Their argument was simple and compelling. A sea-level canal requires no locks, no mechanical systems, no vulnerable gates that could fail. Ships just sail straight through. It worked at Suez, why not here? Plus, there's something elegantly simple about it. No moving parts means fewer things that can break. On the other side stood the lock advocates, led by Chief Engineer John Stevens and his successor, George Goethals. Their argument was equally compelling, but more complex. Fighting the mountain is insane. Instead of removing hundreds of feet of unstable rock and clay, which the French proved was nearly impossible, why not work with the elevation? Here's where the genius comes in. What if, instead of bringing the canal down to sea level, we bring the ships up to the mountain's level? Use locks to lift ships 85 feet above sea level, let them sail across at that elevation, then lower them back down on the other side. Think about what this means in practical terms. Instead of excavating the Culebra Cut all the way down to sea level, removing hundreds of millions of additional cubic yards of unstable material that would keep sliding back anyway, you only need to cut down to 85 feet above sea level. That's roughly a 65% reduction in excavation at the most difficult section. But locks aren't simple. Each lock chamber had to be massive, 1,000 feet long, 110 feet wide, and 85 feet deep when empty. For perspective, that's longer than 3 football fields. These would be the largest locks ever built by a factor of 3. Nothing even close to this scale had ever been attempted. The engineering challenges were staggering. First, you need to fill and empty these enormous chambers efficiently. Each time a ship passes through, you're moving millions of gallons of water. Do it wrong, and you either take forever, creating massive shipping delays, or you create turbulence that could damage ships. The solution? Gravity. The entire lock system operates on gravity alone. No pumps required. Water flows from Gatún Lake through massive culverts built into the lock walls and floors. These culverts are 14 feet in diameter, large enough to drive a truck through. When valves open, water rushes in or drains out through these passages, filling or emptying a chamber in just 8 minutes. Let me put that in perspective. Each lock chamber holds approximately 26 million gallons of water. Filling that volume in 8 minutes requires moving over 3 million gallons per minute. That's roughly equivalent to emptying an Olympic swimming pool every 15 seconds. But here's the brilliant part. The water isn't pumped. It simply flows downhill from Gatún Lake, which sits 85 feet above sea level. Every time a ship goes through, 52 million gallons of fresh water flow from the lake through the locks and into the ocean. That water is never recovered or recycled. It's simply replaced by rainfall feeding into the lake. Panama's extreme rainfall, which was such a nightmare for construction, became the system's power source. The lock gates themselves are engineering marvels. Each gate is 65 feet wide, 7 feet thick, and ranges from 47 to 82 feet tall, depending on its position. They weigh between 400 and 700 tons each. Despite this massive weight, they're so perfectly balanced that a single 40-horsepower motor can open or close them. The gates are built in pairs and meet in a V shape pointing upstream. Why? Because water pressure pushes them together, making them stronger the more force is applied. It's a self-reinforcing design. The very thing trying to break through actually holds it closed. Brilliant. Now, designing this system was one thing. Convincing everyone it would work was another battle entirely. Critics raised valid concerns. What if the gates fail? What if earthquakes damage the locks? What if landslides block the cut even at the reduced depth? What if ships can't handle the elevation changes? The debate reached fever pitch in 1906. President Theodore Roosevelt appointed a board of consulting engineers, 5 Americans and 8 international experts, to make a final recommendation. They visited Panama, reviewed all the data, and debated for months. The vote? 8-5 in favor of sea level. The international experts, many with experience at Suez, couldn't imagine locks on this scale actually working. They recommended continuing the French approach, just with better equipment and disease control. But here's where American engineering confidence, some might say arrogance, came into play. John Stevens, the chief engineer actually on the ground in Panama, basically ignored the consulting board. He went directly to Congress and the president with his recommendation. Locks were the only feasible option. Stevens laid out the numbers. A sea-level canal would require excavating an additional 110 million cubic yards of material from the Culebra Cut alone. At the rate they could safely excavate, given the geological instability, that would add at least 15 years to the project. 15 years of additional cost, additional risk, additional lives in danger. The lock canal could be completed in 8 to 10 years. The excavation was manageable. The technology, while unprecedented in scale, was based on proven principles, and critically, it was adaptable. If problems emerged, adjustments could be made to the lock design much more easily than redesigning a sea-level cut. Congress voted in 1906 to authorize the lock system. It was close. The debate was genuinely uncertain until the final vote. But the decision was made, and suddenly, the entire project transformed. This wasn't just about digging anymore. This was about building the most sophisticated hydraulic system ever conceived. The lock system required 3 separate locations: Gatún locks on the Atlantic side, Pedro Miguel locks, and Miraflores locks on the Pacific side. Ships would be lifted in 3 steps at Gatún, 85 feet total. Then they'd sail across Gatún Lake at that elevation for 23 miles. Then they'd be lowered in 2 stages on the Pacific side. Think about the coordination required. 6 different lock chambers, 12 pairs of massive gates, hundreds of valves, miles of culverts, all needing to work in perfect harmony. One failure anywhere could shut down global shipping. But here's what sealed the decision for me, and probably for Congress too: flexibility. A lock system could handle different water levels on each ocean side. And yes, the Pacific and Atlantic sides of Panama have different tidal ranges. It could manage the variable flow of the Chagres River. It provided control over what was otherwise an uncontrollable environment. The sea level option was fighting nature. The lock option was harnessing it. So we've journeyed through disease-ridden jungles, catastrophic failures, revolutionary medical breakthroughs, and unprecedented engineering decisions. But here's the question that really matters. Why should you care about a canal built over a century ago? Because the Panama Canal isn't just history. It's a living testament to how human ingenuity solves impossible problems. And the lessons learned there? They're still shaping how we build the world today. Let's start with the numbers that prove this canal's ongoing relevance. Right now, as we speak, approximately 14,000 ships pass through the Panama Canal every single year. That's roughly 40 ships per day. These aren't small vessels either. We're talking massive container ships carrying everything from electronics to automobiles, oil tankers, cruise ships with thousands of passengers. Here's what blows my mind. About 6% of all global maritime trade passes through this 50-mile waterway. 6%. That's roughly 270 million tons of cargo annually. Without the canal, every one of those ships would need to sail an additional 8,000 miles around South America's Cape Horn, adding weeks to journey times and burning millions of additional gallons of fuel. The economic impact? Conservative estimates put it at over $2 billion annually in tolls alone. But the real value is in the trade it enables. The canal saves the global economy tens of billions of dollars every year in reduced shipping costs, faster delivery times, and decreased fuel consumption. But let's talk about what the canal really gave us: engineering innovations that changed everything. First, project management at an unprecedented scale. The Panama Canal required coordinating 30,000 workers from 97 different countries, managing thousands of pieces of equipment, synchronizing dozens of simultaneous construction sites, and maintaining supply chains stretching across continents. This level of complexity had never been attempted before. The solutions developed in Panama became the foundation for modern, large-scale project management. The use of detailed scheduling systems, the coordination of multiple specialized teams, the integration of different engineering disciplines, these weren't common practices before Panama. Now, they're standard procedure for every major infrastructure project worldwide. Second, hydraulic engineering reached new heights, literally. The lock system's use of gravity-fed water movement influenced dam design, irrigation systems, and water management projects globally. The principles of massive water control developed at Gatún influenced everything from the Hoover Dam to modern flood control systems. But here's something fascinating. The canal is still evolving. In 2016, after nearly a decade of construction, a third set of locks opened. These new locks are even larger, 1,400 feet long, 180 feet wide, 60 feet deep. They can handle new Panamax ships carrying 3 times the cargo of the original maximum. Why expand? Because ship sizes have grown exponentially since 1914. The original locks limited global ship design for a century, literally. Shipping companies built vessels specifically sized to fit through Panama. It was the ultimate engineering constraint shaping global commerce. The expansion project itself cost over $5 billion and required innovations the original builders couldn't have imagined. Modern engineers used computational modeling to analyze water flow, advanced materials to resist saltwater corrosion, and construction techniques that minimized environmental impact. Yet they were building on the same fundamental principles established a century earlier. Here's what really impresses me. The original concrete used in the first locks is still structurally sound. Think about that. Concrete poured between 1907 and 1913 is still performing its critical function over 100 years later, despite constant exposure to water, tropical heat, and enormous mechanical stress. The quality control and material science applied then set standards we still reference today. The environmental lessons are equally relevant. The creation of Gatún Lake, which we didn't fully cover but is crucial to the lock system, required flooding over 160 square miles of rainforest. It was one of the largest man-made environmental changes in history at that time. The ecological impact, both positive and negative, taught engineers that massive infrastructure projects have consequences far beyond their immediate construction. Modern environmental impact assessments, required for virtually every major project today, have their roots in lessons learned from Panama's ecosystem disruption. We learned you can't just change geography without changing everything that depends on it. But perhaps the most relevant legacy is this. Sometimes the solution isn't to overpower nature, it's to work with it. The French tried to force a sea-level canal through a mountain. They failed. The Americans designed a system that used the mountain's elevation, harnessed the region's massive rainfall, and turned geographical obstacles into operational advantages. This philosophy, adaptive engineering rather than brute force, now influences everything from sustainable architecture to renewable energy systems. We build with the environment, not just against it. The medical revolution deserves mention too. Dr. Gorgas's mosquito control methods became the template for tropical disease management worldwide. The World Health Organization's malaria eradication programs, they're based on principles proven in Panama. Every tropical construction project since, from roads in Africa to cities in Southeast Asia, has benefited from understanding that worker health is infrastructure. And here's something current. Climate change is affecting the canal right now. Panama's rainfall patterns are shifting. Droughts are becoming more severe, reducing Gatún Lake's water levels. Remember, every ship transit uses 52 million gallons of fresh water. When the lake drops, ship transits must be restricted, which affects global shipping. Engineers are currently developing solutions, water-saving basins that recycle lock water, alternative reservoir systems, even weather modification studies. The canal that seemed permanent is now adapting to a changing climate, proving that engineering is never truly finished. It's always evolving. So what's the ultimate lesson here? The Panama Canal shows us that impossible is just another engineering challenge waiting for the right combination of innovation, persistence, and adaptability. It took catastrophic failure, revolutionary medical science, unprecedented construction techniques, and the coordination of thousands of people to succeed. But succeed it did. And every time a massive container ship glides smoothly through those locks, rising 85 feet in minutes, sailing across a man-made lake carved from jungle, then descending gently to continue its journey, that's not just commerce happening. That's 100 years of engineering wisdom still working exactly as designed. The Panama Canal reminds us that the greatest achievements come not from avoiding difficult challenges, but from approaching them with creativity, learning from failures, and building solutions that last not just years, but centuries. And that right there is why this century-old canal still matters today. Because the principles that made it possible, innovation, adaptation, and the refusal to accept impossible, those are timeless.